Hello again, folks, in 113. Today we're going to be covering section 1.1 and 1.2. It's a bit bright here, so I'm going to have to adjust the lights. Let me start with this. Normally, if we were in person, I would give you a packet at the beginning of each class that consists of the material that outlines the subject. So I'm going to point out on Canvas where you could print this yourself. Right? It doesn't have to be in color. I know that can get expensive, but do try to print out some of these because I meant it to help you serve as scaffolding. Right? This is a diagram that I made. Very often when you're teaching a subject like math, there's a lot of unique vocabulary, which it helps to compile. And then, as is often the case in math, there's an abbreviation. And then we will try to describe, in plainer terms, what it actually means. So we'll use that right off the bat. This is a diagram I swiped from this textbook, I believe. Right? These are the place values that you ought to know by heart. Right? Tenths place, hundredths place, thousandths place, 10,000ths place, 100,000ths place, millionths place, right? It goes beyond that, of course, to the right of the decimal point. But know at least in this spectrum, this interval, to the right, and the names, of course, to the left, ones, tens, hundreds, and so forth. Right? When you have to round, it is especially important to know what is being referred to. When we get into section 1.2, this will serve as an overview when you're asked to round something versus when you're asked to estimate. Okay? This is a procedure I follow myself when I have to do rounding. And this I want to impress upon you. This is not from your book, I don't believe. This is a copy of the multiplication tables. In the past 20 or so years, the academic establishment has moved away from getting students to memorize this. I think for the argument that, well, they have calculators, so why would they need that? And unfortunately, it is a grave disservice to tell your students, especially earlier on, that they don't need to do something, because this is the foundational information in math, right? So it's sort of like, maybe not as egregious, but telling a little kid, you don't need to know the alphabet, and then expecting them to be able to write, So that was very short-sighted. So we will fix the problem, right? In the long run, whether you know these by heart or not, right? Don't project that onto the next generation, right? In the position of math teacher, you must convince your students, all right, to know this information because so much is dependent upon it. Okay, so have that handy. The old days, this is regarded nowadays as corporal punishment, which is idiotic. But what you would do if you wanted to memorize multiplication tables was that you would physically write it because it makes a stronger connection when you write something. All right, 12 times 2 is 24, 12 times 2 is 24, 12 times 2 is 24, and so forth. Then you do 12 times 3 is 36, and so forth. Right? How does a person learn how to spell? All right? You write it several times, right? That's still a valuable skill to teach little kids, right? So don't shy away from that, whatever anybody says. All right. And these are the examples from the book. I snipped them out and attached them as a PDF. All right. Now, that's the packet that I would have given you were we in person. Let me show you where you can look for these online to print. And I'll adjust the lights. So I gotta move my camera, it looks like. Yeah, that's way off the mark there. Is that blurry? That's okay. to do. It's morning as I'm recording here, so I have a lot of ambient light here. I hope that helps. That's a bit better. Alright, here is the student view of our Canvas page for MAT-113, Mathematical Structures 1. Alright. The way I made it is the syllabus is the front page. It is the same as if you hit the button that says home. Alright. Here's the syllabus, of course, which you might have by now, because this is for Thursday's class. And if you scroll down, you'll notice here is an overview of our schedule. So this being for Thursday the 27th, we're going to cover section 1.1 and 1.2. Right? I would prefer, if you notice, over the long run that we just do one topic per day. But the way that it works out, it's best to have these two things bunched together, and these two, right? So that we have freed up the space and time for much later in the semester when we get to probability. Okay. All right. Now, as for those handouts that I was mentioning, if you would like to print any of them and you have free reign to do so, they're all here, right? Chapter 1, 6, and 10 is the first batch. And they're more or less grouped according to a color, not any specific color, but you notice in here it says section 1.1 and 1.2. Anything that is that same shade is for the same day, right? In the next batch underneath it, I tried to make a space, obviously. These are purple. This would be for the subsequent section, and then the class after that, and then the class after that. Okay, so you don't have to dig too much. Right? It's just this this blue range of things. Right? These are called new because I had entered them more recently. All right. You could just look at it instead of printing it if you'd like. I think my camera is going to do it a disservice though, so I'm going to just use it from the files that I have on my own computer. There you have the same handout. Alright, so having said that, let me just show you my own copy here, and I'll get going with this. Where did I put that? Since I'm like me, I didn't do it, huh? Alright, well, I'm just going to borrow it then. Okay. Let's see. I'll leave it like that. There you go. Can you ask me that? No, I don't want that. Yeah. Okay, that's better. Slightly more aesthetically pleasing, I hope. Alright. You, of course, if you have this printed, you're welcome to annotate, write all over it. Especially if there's a typo or whatever. Alright, so let me get through this. Alright, basically for section 1.1, what we're going to be talking about initially are different thought processes. Alright, I like one of the quotations from our book, which refers to inductive reasoning versus deductive reasoning as more or less the difference between thinking like Sherlock, who of course was not a real person, a fictional character, and Aristotle, who was an actual person. Right. Aristotle, the Greek philosopher from don't quote me on this, about 300 BC, something like that. And Sherlock, the 19th century detective. All right. More or less, inductive reasoning is something you could say is thinking like a scientist. It's a specific thought process, a direction, if you will. Right? Deductive reasoning is more or less thinking like a mathematician, and I would add one other thing too. A specific type of mathematician, someone known as a geometer, a Greek mathematician, right, from the old days. Right? Here is the thought process as sort of a linear paradigm. And just move this. This is the train of thought, all right? What you're going to start with in the case of inductive reasoning process is that you're going to start with usually given specific examples, or if you're running an experiment, observations, right, of something happening, observations of a phenomenon, right? The goal in inductive reasoning is to form a general conclusion, right, or to establish a model or a theory, right? So you have specific examples, that's the operative term there, specific, and you end with general conclusions. Right? Deductive reasoning is basically the opposite of that. That's to oversimplify though. You start with a general statement, a law, a rule, all right, some principle in math. That's why I say it's usually applied to geometry. Right? If you've ever had high school math in the United States, it's usually the bane of 10th graders' existence, right, is geometric proofs and stuff like that, not to dissuade you. But anyhow, you start with those given set of rules, if you will, right, and you try to form a specific conclusion, some unique specific example. You know, why is this a triangle, given the theorems of triangles, right? So you start with something general, you end with a specific conclusion. Right? You want to apply the rules to solve a specific problem. Okay. Now to add to this, and I'm sorry for the glare. In math, I try to keep these things sort of in a column and of the same color. You may notice these are red as well. In math, science, and statistics, this often takes the form of writing equations, that is to form a general conclusion, right? A model, right? Or formula. This is for the purpose of forming a prediction, right? About the future. Math is its own kind of sorcery in that sense, right? You try to predict the future, right? The thing is, your predictions may not be quite right? Answers can be true or false, but at least you have something, right? And the more data that you have, the more likely something will, your prediction will be correct. Right? The better the model, the more data. Which is why it's good to do the same experiment many times. In math, this process, right, to form specific conclusions, is often used to prove something. Right? There's again the operative term. Think, if you want to sort of summarize, right? When you think inductively, you want to form a prediction. Right? When you think deductively, you want to prove something. Right? As I mentioned, geometric proofs. This is through the process of pure reason, though. It's all going on in here, all right? Rather than through a physical experiment, per se. Right. Now, interestingly, you might hear these two paradigms thrown around, right? Especially as a kid going through school. There is, of course, the scientific method. And then, for comparison, the axiomatic method, which predates the scientific method. Right? The scientific method, again, inductive reasoning. right, is a cyclical process. All right, it's not very well drawn here, but you start with an observation about some phenomenon, natural phenomenon usually, right? And this leads to a question, right? Now, to follow the train of thought, the question inspires an answer, but if the answer is not tested yet, it's referred to as a hypothesis, right? A hypothesis is a temporary answer, right? It isn't necessarily correct, right? It's just the best guess, if you will, right? And if you have that temporary answer, once you have that temporary answer, you could design an experiment to test the hypothesis, right? Which is why I said that this is a cyclical process, because if you design an experiment and then you run the experiment, it naturally leads to phenomenon, right? Phenomena, plural, right? Which you will make observations of, which will often lead to more questions, which will again lead to maybe a refined answer. That's usually the goal, right? To get better and better guesses, if you will, right? Until you come to something that seems pretty much the truth, right? I put this in blue adjacent to hypothesis because it's synonymous. In math speak, for lack of a better phrase, the equivalent of a hypothesis might be referred to as a conjecture, right? In that a hypothesis is not necessarily true. It's not tested yet, right? To say if it is or it isn't, right? A conjecture is an unproven answer, right? So it is similar enough to put them on the same tier, as you could say, right? This cyclical process, known as the scientific method, is how theories are born, refined, and eventually, in some cases, overturned, right? Now, as far as the axiomatic method is concerned, we're using a modern definition, right, versus that of Euclid, right? Because Euclid is the originator of this, thought to be. The modern definition of an axiom is as follows. An axiom is a foundational self-evident premise. Something is what it is. Like, say, for example, a mathematical point, right, is the most fundamental, for lack of particle, in a physical sense, object, idea in geometry, all right? A line would be based upon points, right? It's a bunch of points that are in a line, something like that. Anyhow, there's nothing less plain to describe an individual point, right? So it is used as more or less the foundational concept, all right? An axiom, all right? It's self-evident, it is what it is, and it's used to define things that are more complicated, things that are contingent upon it, right? Like lines, for example, right? Now, what you see over here is more or less the original Euclidean way of thinking about it and the more modern way of thinking about it. It's the same thing, it's a two-step linear process, but we've changed some of the vocabulary, right? Classically, undefined terms like these basic fundamental concepts were known as axioms, and they are used to create formal definitions about which things are more, are contingent, right? Things that are contingent upon the more basic concept are use the axioms to form their definitions, right? All right. Now, the terminology nowadays is that the important undefined concepts are known as postulates, right? And the postulates are used to form theorems, right? These are proven again by deductive reasoning with axioms, right? The axiom is the basic idea, right? The basic definition, right? And the basic definition is used to make the more formal definition, something, all right, more complicated, the more complex definitions, right? Postulates is the more chic phrase, if you will, right, for axiom. All right. So again, as an overview, I'm just going to back this off so you can see it all at once. These are the two trains of thought. All right. Inductive reasoning on this left side here. Deductive reasoning on this right side here. All right. What most is akin to the concept of inductive reasoning would be scientific method, i.e. to think like a scientist. Right? What is most akin to deductive reasoning would be to think like Euclid, or a geometer, a mathematician of geometry. Right? Okay, so keep these two ideas in the back of your head. Right? You'll get some questions that will basically ask you, is this deductive or deductive? Right? It's all about where you start and where you're going, what the goal is. Okay. Now, let me just put this in here, just for a reason I don't have it. Yeah. And we'll go back here. I'll do that. Okay, my handout's in here. All right. Let me get some terminology out of the way. I kind of alluded to this already. So I want to use that scaffolding I mentioned that I will use a lot throughout the semester. These tables that you could use to collect vocabulary. Is that a little bit too much? I think so. Back that off a wee bit. There you go. No, I don't like that feature. Alright. Let's start with this. You already have this on this piece of paper, but these are similar enough to group them together. I hate hypothesis, i.e. a conjecture. One might argue, oh, they're not exactly the same thing. They're similar enough. Right? Know these words. Right? A hypothesis or a conjecture, depending upon whether you're a math person or, say, a scientist, which are almost the same thing as well, is a prediction. Right? Based upon specific observations. Right, and I really want to impress upon you that the prediction, which is a temporary answer, right, may be true or false. Because until something is thoroughly tested, right, we don't know if it's true or not. Right? It's just an educated guess for the time being. Right? Often is the case, you look for something to prove whether something is, well, to prove something false, we look for something known as a counter example in math. This blue marker is dying. So I'm going to put this here. A counter example is just one. So, an example that utterly proves a conjecture false. You only need one example to do so. Only one is necessary, okay? To prove a conjecture false, you need one example that overturns the prediction. Okay. Now there is some other vocabulary that is a little less complicated, so let's get into that. It's going to be important later as we get into set theory, so I should probably give you this now. All right. I'm going to erase this and maybe expand it just slightly because I need the space for more terms. Ooh, that's sticky. It's an unfortunate thing about blue. Right. It's rather tenacious, as you can see. So perhaps I shouldn't write that one. All the other colors are cooperative today, not blue. It's not permanent, I swear. I don't want to keep doing that, so I'm not going to make the same mistake twice. Put that away. Free enough. So let me see. Alright, I'm going to put this like so. You get the idea. We'll have the vocabulary term, the concept. If there is an abbreviation, I'll try to illustrate it here, and then briefly describe the same. Alright, let's start with this. Through my own life in school, I've heard people, I remember my teachers talking about something called natural numbers. Alright? And even though they described it to me, I never really appreciated what they meant by that. So, natural numbers are labeled as such. Right? Because they're natural to a human. It's basically referring to the kind of things that you would count using your hands. All right? They're natural because they're intuitive, right? 1, 2, 3, 4, 5. You don't count negatives with your hands. I mean, you could really if you wanted to be creative, but nobody does that, at least not initially. Right? So the natural numbers are otherwise referred to as the counting numbers. The kind of thing that you would use your hands with. I'm using hands to illustrate. Okay. There is an abbreviation for it. All right. The concept is so fundamentally important that often it's abbreviated, the entirety of them, by the capital letter N. Right? If a person, and that's a generalization, right? If a person wanted to illustrate the basic pattern without just simply referring to it by name, they would put it in something called set notation. This is going to come back to haunt us later. Set notation is when you see something in fancy braces listed like so. I'm putting question marks because those are the contents, otherwise known as the elements of the set. Right? So in the case of the natural numbers, what you might see is fancy braces, and then the beginning of natural numbers is the number 1. 1, 2, 3. Now you can't, because it represents the entirety of them, you can't write all of them. It would be impossible. So usually what you do is after the last comma is you put 3 periods in succession known as ellipses to indicate that the pattern stretches beyond just what is visible. Right? These are known as ellipses. Right? The 3 periods, right? And it's meant to signify that more follows. Okay? Now, for the sake of contrast, right, we have the natural numbers and then this next concept, which is the even numbers. The even numbers, I suppose, could be abbreviated by a capital letter E, but I don't know if that is formal enough. I'm not sure that people have agreed on that. There's no consensus. So I'm going to list them in set notation in roster style, which is to say, well, what's the first even number? 2, 4, 6, 8, and so forth, right? One might argue that 0 is also an even number. But if we're just sticking with this concept of natural numbers, 1 being the beginning, we're going to start with 2 for now. Here is the better definition of them. These are natural numbers divisible by 2, which begs, or I shouldn't say begs the question, but leads to the next question. Well, what does it mean to be divisible? Right? Divisible. Right. Essentially, I'm going to abbreviate that as best I can here. If one thing is divisible by another. If A divided by B results in remainder 0. Right. A more plain way of speaking of divisibility is to say when two numbers divide nicely, meaning that there's no remainder, no fraction, no decimal, it just terminates at the ones place. Okay? Right. I'm going to sort of elaborate on this because you do have to be very careful on how you phrase it in English. Right. So I'm going to try to describe this. I may need a better marker. Sorry. A, it's about the same, is divisible by B, meaning the second thing in sequence here. Remember, these are not commutative. The order definitely matters. A is divisible by B if the remainder is 0. i.e. divides nicely. That's just my own way of referring to it, but it's not very formal to say it that way. I think it just gets at the feeling. All right. Now, make this distinction. Almost anything is dividable by anything else. You can't. The one exception is that you can't divide by 0. You could divide into 0, can't divide by it. Right? It would be undefined. All right. But not fewer things even still are divisible. There's dividable and then there's divisible. We're talking about divisible, right? For the sake of a definition. You notice how this is unfolding. The more axiomatic, more basic concept as this is unfurling are the natural numbers, because you're using the natural numbers to describe the more complex idea, right? Even numbers are a subset, a more specific example of the natural numbers. Those things that are divisible by 2. Of course, you then need to explore what does it mean to be divisible. It means that it divides nicely. Two things divide nicely. Right. Now, because I'm a little short for space, I'm going to add one more thing here, and then we'll stop. All right, in terms of terminology. The odd numbers. The odd numbers are 1, 3, 5, 7, 9. And it would go beyond that. 2, 4, 6, 8 is just the first 4, all right, of the evens. 1, 3, 5, 7, 9 is just the first 5 of the odd numbers, all right. These, sticking with the same idea, axiomatically, if you will, these are natural numbers not divisible by 2. There's lots of ways you can define things, right? But if this is the most basic concept, we could use it to explain the more complicated things. That's the principle of axiomatic method, if you will. Okay? So, even numbers are natural numbers divisible by 2. Odd numbers, in our definition, are natural numbers not divisible by 2. Right? And this is what they look like, respectively. Okay. My computer's falling asleep here. Alright, let's do some examples. Alright, again, in the packet of material that you could print, I'm just going to sort of flash it really quickly. There are these green examples with the solutions included in this case. I swiped these from the book and plastered them onto a document so that you can print it, okay? Let's look at these examples. We've gotten the terminology out of the way and the thought processes. Okay, I'm going to have to erase a bit, so humor me for a moment. Cooperative ink. Alright. Because I don't want to give away the store, I'm going to purposely obscure part of this. In the profession of teaching, you have to be somewhat of a showman and to know what not to show people immediately. Alright, now it might be a little hard to see because of the glare of the sunlight. I apologize. Let me read you this and I'll try to expand it just enough to make it more visible. We'll go through this. Okay. An example of inductive reasoning, right? The product of two odd numbers. If two odd numbers are multiplied together, will the product always be an odd number, right? What we might do to form a hypothesis, right, or a conjecture if you prefer, in math speak, is test a few examples of odd numbers multiplied together. So you might try a few. This is example 1 here. Test a few is the name of the game. Alright, so if the odd numbers we know of are 1, 3, 5, 7, 9, we just got through it, right? We'll try a couple of these in sequence, right, as a product. 1 times 3, 3 times 5, 5 times 7, doesn't have to be in this order, they just have to be odd. 7 times 9, 9 times 11, and we'll see what we get. Alright, so what do you get as a result of having done these two odd numbers as a product? 1 times 3 is 3, which is indeed an odd number. All right, 3 times 5 is 15, which is indeed an odd number. 5 times 7 is 35, also odd. 7 times 9 is 63, also odd. 9 times 11 is 99, also odd. All right. By definition, all right, they're not divisible by 2. Only evens are divisible by 2. Right. So we do get all odd numbers. All odd products. Right? So what can we say? Right? We can say, we can conjecture that the product will always be an odd, just based upon these few examples. Now, is that necessarily true? No, because we haven't tested all of them in theory. Remember, numbers are infinite. But our educated guess is that yes, they will produce always an odd number. Right. The best thing is to remain skeptical. All right, just keep testing something, and then you will have more and more certitude. Right, you'll be more comfortable with your educated guess. Okay, this is an example of inductive reasoning again because we're using specific examples to form a general conclusion. Right. All right. Let's take a look at example 2 here. All right. If an odd number and an even number are added, all right, will the sum always be an odd number or an even number? Well, if we're following the course of the train of thought, the paradigm, the thought process of inductive reasoning, right, then what we might do is, again, try some specific examples and look for a pattern. Try a few. All right, so we need an odd number and an even number that we're going to add to form a sum. All right, so just to remind you, here are the odds: 1, 3, 5, 7, 9, and so forth. And here are the evens, just for reference: 2, 4, 6, 8, and so forth. And we're going to take 2 in tandem and add them. So I'm going to put them here just for the sake of time. 1, 3, 5, 7, 9. This might be overkill. I'll try 2, 4, 6, 8, and then technically 10 for this last one. And I'll add them. So plus, 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 plus. Just to get that out of the way. Okay. What do we get in each of these cases? Well, 1 plus 2 is 3. An odd and an even produces an odd in this case. 3 plus 4 is 7. An odd and an even produces 7. 5 plus 6 is 11, also odd. 7 plus 8 is 15, also odd. 9 plus 10 is 19, also odd. So, once again, based upon just these few examples, because we cannot possibly test all combinations, we would never finish. All right, one could make the conjecture that it always produces an odd number. Right? The sum of an odd and even produces an odd. Okay? specifically, right? That's what we would have to conclude just based upon these few examples, because these are in fact all odd outcomes here. All right. This is again inductive reasoning because we're using specific examples to form a general conclusion. All right. Now if you skip a little bit, because in the packet I did that on purpose. We're going to skip to the latter half of this to get to deductive things. To illustrate deductive examples. And I'm going to need the space, so I'm going to scoop this up a wee bit. Take a sip of water too. Okay. Now, in this case, it again might be hard to see with the glare. Pick any number, multiply the number by 4, add 2 to the product, divide the sum. I think that might be cut off a little bit, is it? Yeah, it's not quite visible because I have it expanded, so let me just zoom out just a wee bit. There you go. Divide the sum by 2 and subtract 1 from the quotient. Repeat this procedure for several different numbers and then make a conjecture about the relationship between the original number and the final number. Now, it would be quite tedious to have to do this multiple times, being that this is multi-operational. So what we're going to do is we're going to take advantage, all right? When we get into section 1.3, and I want to say 6.3, which is the subject for next week, all right? That's about essentially dissecting word problems. So here's something of a preview, all right? If you have something like this, a word problem that is not too bad, but a little complicated, right? What you'll do is get in the habit of procedurally annotating as you're reading it, right? Pick any number. What's an abbreviation for the word number? N, right? Multiply the number by 4, right? Multiplication is an operation. So you're going to multiply by 4, right? You're going to add 2. Adding is that symbol 2, right? You're going to divide by the sum. That's an abbreviation for that, right? A sum is a group of things, so I'm going to purposely put them in parentheses. Right now I don't know what the sum is, so I'm just going to put question mark plus question mark. Divide by, that much. Divide the sum by 2. That's going to have to be finagled a little bit because the order is backwards the way I wrote it, right? Divide by 2 means essentially that this symbol is going to go in between the sum and the number 2, right? And subtract 1, that's minus 1, right? From the quotient, right? If we're going to use deductive reasoning, and this is meant to illustrate that, then the thought process, the train of thought, is that we have a general statement and we're going to form a specific conclusion. Right? The cheat that we're going to use is that our general statement is going to be in the form of an equation. Okay? Because using the letter n will generalize any number, right? So we just have to arrange it in a nice way. This is verbally describing the multi-operational process. Rather than just talk about something verbally, we can refine it, a little slow process, down to the essential and then write it in the abbreviations using these math symbols in some arrangement. All right? So, you may start out with something that is gobbledygook, that's more verbal than it is abbreviated, but don't feel bad, all right? That's what happened to anyone, including myself, right? So here's what we're going to do. We're going to take some of these abbreviations and begin to arrange them, right? We're going to, now, if we follow the instruction further, it says, repeat this process for several different numbers and then make a conjecture about the relationship between the original number and the final number. All right. If we're going to write an equation, what symbol must we have in an equation? It's in its name, an equal sign, right? So, I'm going to sort of make a left side of the equation and the right side of the equation. And on the right side, I'm going to try to arrange this stuff here. All right, a number times 4. I'm going to start with that. So, point number 1 here is n times 4. Then it says, that much is accounted for, that we would have to add 2 to the product. This is a product because it's a multiplication. So I'm going to group these because we're referring to something as a product. And a product is the result of this, which we can't see yet. So plus 2 would be the next part of that. Okay? Then it goes on to say that you would divide the sum, which would be, this entire thing would be a sum, because it's that product plus is the sum 2. Divide it by the number 2. So this, I'm going to use this style of division rather than the traditional style of division. Divide by 2, right? That forms a quotient, right? This entire thing is a quotient. All right? The top part that consists of a product and a sum is now divided by 2. The whole kit and caboodle would be a quotient, right? And then subtract 1 from the quotient. So I'm a little shy of space here. So if I just move this over a wee bit, I'll just put my little equals over here. To subtract 1 would be to put a minus 1 out here. All right? That is the essential of what is being described in the paragraph. It's not perfect, but we could whittle it down slowly but surely. That's what anybody does, right? So don't feel bad if you've got something sloppy as you see that I have, right? One thing about math is that it requires stick-to-itiveness, right? Tenacity, right? Grit, right? Which is something that anyone can cultivate. If you stick something through, if you're determined enough, you could make it better and better and better. You could lead to constant improvement, right? We have to cultivate that in our society because it's not a cultural norm here to stick with something when we should. All right, now I'm going to take this and I'm going to rewrite it up someplace, perhaps, without erasing too much to make this better than you see it here. Trying to set a good example, basically. All right. A more concise way of writing n times 4, you may remember if you've seen algebra, is to not use the multiplication x, but to sometimes use dot. And then good etiquette, which is more or less like sipping tea with your pinky in the air, is putting the number in front of the letter. Right? So I'm going to do that here. 4n is going to stand in place of n times 4 with the parentheses, because although that is explicit, it's a little bit more gross, more complicated. All right? That plus 2 is the top part of this. All right? Now, it's part of a quotient, so these two things still have to be on top of this line to stand in place of the traditional division symbol. It's divided by 2, so we're 2 down here. And then the rest of this was to subtract 1. So off to the side here would be minus 1. All right. Here is, although it is incomplete, half of our equation. All right. All right. If you had to choose, technically, between referring to this as an equation and an expression, in this form where there is nothing actually sitting here yet, this would be more appropriately referred to as an expression. It's only when you have something over here finally that it would be appropriate to have this equal sign. Okay? But it nonetheless is a general statement, right? A model that we could use to now repeat the process using several different numbers in place of n to see what we get, right? So I'm going to do that now, all right? If, I'm going to put it here, 4n plus 2 over 1 minus 1 were tested, or utilized, perhaps would be a better way of speaking about it. We can see what we're going to get in each of these cases. Expression, expression, expression. All right? Let's say that I substituted, it doesn't specify that it has to be odd or even, any number. I'm going to go with the easiest number in the world, 1 in here. And I'd have to follow the order of operations, which is, again, something that I shouldn't take for granted that you know. But I'll remind you, you're going to follow the order of operations. That is the specific procedure when you have a multi-operational problem for deciding whether you multiply, add, subtract, or whatever. You do multiplication before you do addition, right? In this case, because of the way it's arranged, you can do division immediately after it. Okay. So 4 times 1 is just 4. 4 plus 2 is 6. 6 divided by 1 is 6. 6 minus 1 is equal to 5. Save that number. Oh, wait, I missed one thing. Sorry. Shame, shame. That's a 2 down here, and I fudged it and I put a different number, so sorry. That's going to change things. What's 6 divided by 2? 3, not 6. Alright. What's 3 minus 1? 2. Okay. Now, it probably would be a good idea, since they're asking us, make a conjecture about the relationship between the original number and the final number. This is the final number in this equation. All right. So the original number in this case was the number 1. The final number, as you can see, is 2. All right. Let's do another one. So we're going to do something not too much more complicated, but if I substituted a 2 in here, all right, do the multiplication first, because it's the top of this ratio, add 2, and then divide by 1, in that order. All right. 4 times 2 is 8. 8 plus 2 is 10, and that's a 2 again, ding dong. 2, sorry, 2. All right. 10 divided by 2 is 5. 5 minus 1 is 4. Now again, for the sake of analysis, the original number was 2 that I substituted here. And the result, the final number, is 4. Let's do this one more time. I'll do the next easiest number, which would be 3. That's another thing. If you're a little concerned about, well, what numbers should I choose when I'm left to my own devices? Always make it easiest on yourself, right? Any math person would. Use 0, 1, 2, 3 in that order, right? When you get into graphing, you might use some negative numbers as well, but the smaller ones, you know, smaller in magnitude, right? So that's a sloppily writ 4, but that is indeed a 4 there. I'm gonna check the time here. Okay. Now, 4 times 3 is 12. 12 plus 2 is 14. 14 divided by 2 is 7. And 7 minus 1 is 6. All right. So again, for the sake of comparison, the original number is 3, and the final number is 6. All right? Use 1, get 2. Use 2, get 4. Use 3, get 6. So what could we conjecture, having used this general statement? This is the general statement. Right? Right. And it's technically an equation until it actually is solved. I mean, it's technically, this much of it, I'm just driving myself nuts. This is an expression by itself. It becomes an equation once you have something on the opposite side here. Okay? The conjecture would be, that you get double every time, right? Use a number, you get double as a result of this rule, so to speak, right? This multi-operational rule. Okay. To summarize, we get doubled. There's a more eloquent way to say that, but that is essentially what's going on here. Conjecture is we get double whatever the original. Right, as a result of this multi-operational process. Okay? Now let's move on to section 1-2, and to do that I want to remind you of place values, right, to start with. It is essential, right, that a person know these by heart. Right? Especially if you're teaching little kids. I mean, part of the goal when kids are little, right, is to get them to memorize fundamental facts, right? That's why it's silly to tell a kid, oh, don't memorize something because you could use a calculator. Yeah, a calculator is for making our lives less miserable when we have to do a lot of calculations that are the same over and over again, right? But when you're a little kid, you need to memorize fundamental facts because whatever follows is contingent upon that. All right? So, here's what the state of New Jersey, at least in its infinite wisdom, has decided is the range in which you should know the names here, the place values. In order to round correctly, when the instructions are given, you need to be able to identify these places. Right? Now remember, virtually everybody to the left of the decimal point, that's what we use in the United States, right, knows that this is the ones, tens, hundreds, thousands, 10,000s, 100,000s, millions to the left, right, of the decimal point. Shall we say regular? Right. But, right, less, unfortunately, people know that to the right we have the suffixes THS. the THSs, if you will, right? There's no one-ths place, right? There's just ones, and then sort of the parallel, the mirror dimension here of tens is tenths, right? Hundreds is hundredths, right? Thousand is thousandths, right? It's annoying to say them, granted, hundreds, hundredths, right? THS. Tenths, hundredths, thousandths, 10,000ths, 100,000ths, millions. I bite my tongue every time I do it. All right. Anyway, to the right are the THSs. Okay. Know those by heart, or at least initially have the frame of reference, the picture. Okay. Now, to help summarize, let me show you something that I made. Which I keep having trouble finding. I don't know why I lose it all the time. Gee whiz. Yeah, apparently I didn't put it here. Alright, back to square one. Here's where I'm going to steal it. I posted it here and then I didn't save it, so. I didn't save it to my computer, but I mean. Turn off and then turn it back on. There you go. Yeah, I know. Failed to fetch. Try again. That sad looking chalk is me. Alright. Download. Download. That's the desktop. Alright. Get rid of that. There's one thing I find annoying about Apple computers is the lack of a taskbar. Yeah. Okay, to summarize these concepts, rounding versus estimating. All right, think of them as being procedural. All right. Order makes essentially the difference between these two things. Okay, if you are given, all right, a number, all right, to round to a specific place, or you have done the brute force adding, subtracting, multiplying, or dividing, and then it just behooves you to round after the fact. All right, this is after. You round after. Then you would say that you are simply rounding. All right. If, on the other hand, you round the parts involved, now if in the case of adding they would be called the the addends, right? In the case of multiplication it would be the factors, in the case of division it would be the dividend and the divisor, and in the case of subtraction it would be the subtrahend and the minuend, which is more obscure phrases, right? All right. If you round the parts first, all right, then you are estimating. I put this in specific colors so that you could make the distinction along with me. All right, rounding after is basically just rounding. That is rounding after the operation is just rounding. All right, really rounding strategically before the parts, then following the operations. That's estimating. Okay, so make that distinction. I'm going to back this off a little bit. All right. Now, there are different things that you might do depending upon the operation involved. Right. Let me complete this thought. Sticking with the rounding half of this. Right, this is why I made it blue. Rounding requires a couple of things. Mastery of, as I mentioned, place values. So, again, know the place values by heart. I'm having trouble with my pins don't work here. Know the place values, right, by heart, all right, and then the actual technique involved, all right, which is the next page I'm going to show you, which is, whether you round up or down. multiplication, all right, that's what I was alluding to before. If you're going to involve if you have to multiply something, all right, know your multiplication by heart, please, the tables, all right, and because it's rounding, you have to engage in a little bit of flexibility, all right, which is why several different answers might be acceptable for the same problem, all right. When you're doing estimating, which I'll just put up here, I would maybe apply these different procedures depending upon whether you're adding, subtracting, or multiplying or dividing. All right. When you add or subtract and you're estimating, that you've rounded the parts first and then you've applied the operation of addition or subtraction. These tend to be more consistent, and by that I mean that you're rounding to the same places. So if you're given parts that are, 2 or 3 digits wide, right? You might round them both to the 10th place or the 100th place or so forth, or the ones and the 10th, whatever. You're consistently doing the same thing to each of the parts, all right? When you're multiplying or dividing, these tend to be less consistent and more convenient. By that I mean it's for your own sake of, making it easier on yourself. Because you deal with things that are generally larger when you're dealing with multiplication, right? All right. You round maybe to different places, right? That's why it's less consistent, I would say. Because it makes the multiplication or it makes the division easier, right? Right. How much you estimate differs, how much your estimate differs from the exact answer depends upon the degree of convenience that you've taken, all right? If you rounded things to, really easy numbers, nice round numbers, you might have an answer, but it's drastically different from the exact answer, right? All right. A small difference between the estimate and the exact answer would suggest that you have high accuracy, right? Meaning that you're very close to the exact answer, right? But probably in that case it would be less convenient. That's the trade-off, right? Right? The trade-off for convenience, that is how easy something is when you're working with it, is accuracy. Right? Usually it's the more convenient, the less accurate. One could assume that. Okay? Anyhow, this is an overview of what we're going to do for adding, subtracting, and multiplying and dividing. We're going to be more consistent in the case of adding or subtracting. We're going to be more convenient, right? Well, made it easier on ourselves when we're multiplying or dividing. All right? Now, how you actually round stuff. Take a look at this page, as I tried to summarize. Here. No, I want PDF. Okay. All right. I, for my own sake, have a little procedure like so. Get the gobbledygook out of the way. Right. Estimating involves rounding, so we would need to know how to do that. All right. I underline, because it's not done for you, I underline the place that I'm rounding to, and then I circle the number to the right of it, because it's that circled number that allows me to make a judgment call about how things actually end up. Okay? So here's the two basic rules. If the circled digit is 5 or greater, then you increase the underlined digit by 1. So for example, suppose that I'm going to round to the 10th place. Tenths. Right? And I'll use these figures. Right? 0.46, right? And then 0.44. Right? first of all, if you're rounding to the tenths place, I'm going to underline the tenth place, tenths, which is where the 4 is sitting in both of these cases, right? And then I'm going to circle the number immediately to the right of these to make the judgment call. So I'm going to circle this 6 here to decide what I'm going to do, and I'm going to circle this 4 here to decide what I'm going to do. All right? Now, based upon this circled number, if the circled digit is 5 or greater, and this is the number 6 sitting here, right? Then what am I going to do? I'm going to increase the underlying digit by the amount of 1. That means that the result here is about equal to 0.5. Now you might say, well, this is now only 2 digits wide versus before it was 3 digits wide. If you want to, you could fill in a 0 here. That's what I'm alluding to down here. In any case, every number to the far right of the underlying digit becomes a 0, if it is a convenience for you to write that. Right? You don't have to put it, it's optional in this case. If we were on the left side of the decimal point, you really must put the zeros, because otherwise it looks like just a smaller number. Right? But this is 5/10, right? Or 0.5 if you like. Right? Now over here, 0.44, right? Following the same procedure. If we're rounding to the 10th place, that's underlined 4 here, first place after the decimal, I circle the number immediately to the right of it to make the judgment call, right? And I use the squiggle equals because it's an estimate, right? If the digit is 4 or lower, meaning less than, right, then change the circled digit to a 0. In other words, you don't, when people get confused when you say round down, they go, oh, make that a 3. No, all right? What you're doing is you are just changing this to a number. So if you read it as 44 hundredths, right, this would be 40 hundredths. Okay? That's what's rounded down, right? It's not that you change this to 1 digit lower and make that 0.3 instead. Don't make that mistake, okay? This is rounded up, right? Because you went from essentially 46 to 50, right? It's just that this extra 0 here is more or less optional, okay? So be careful, right? Those are the 2 essential ingredients here, right? 2 essential trains of thought. You have to decide whether you round up in this case or round down in this case based upon the digit that is ironically not the place that you're rounding to, but next to it. Right? That's why I underline and circle. Right? It's more or less to draw my own attention when I do this. Right. Let's do some examples from the packet. All right. Buried in these pages towards the back again is examples like this, estimating, it says it at the top there, and we'll do a few of these, okay? All right. So, gotta get rid of this, and go back to the examples pages. There we go. All right. All right. Take a look at this. I'm sorry, I'm giving away the store here, but I will minimize that. Okay. Okay. Estimating the cost of cupcakes. Sonia decides to purchase cupcakes for a party. Estimate her cost if she purchases 19 cupcakes at $1.95. Now, again, section 1.3, which is forthcoming, and section 6.3, I believe, is in tandem with that, is more or less about the techniques of translating something that is verbal, a word problem, into something that is more symbolic, more mathy, if you will. All right, but we haven't gotten there yet, so we're going to just kind of cheat a little bit. All right, if they're mentioning an estimate, what that is implying that there is an operation involved, right? And that we do the rounding first. Okay, beware. Now, it doesn't explicitly say which operation, namely whether you add, subtract, multiply, or divide. They kind of take it for granted, which is not a good as a teacher, all right, to do. But they do. They take it for granted that you know what would be the most efficient course of action in this case. Right? Now, estimated cost if she purchases 19 cupcakes at $1.95. In theory, think the bill gets larger the more that you buy. Right? How do we make things larger? If we had a choice between adding, subtracting, multiplying, or dividing, the most basic concept would be this makes things bigger, adding, right? However, are we going to add $1.95, $1.95, $1.95, $1.95 for 19 cupcakes? Or is that inefficient, right? A slightly more sophisticated form of adding is multiplying. This is more efficient adding. So, although again, it's not explicitly telling you to multiply, one could infer that. All right. So, the exact answer, and then there's the estimate for the sake of comparison, would be that we would write $1.95 times 19. And we go through the process. Now, could you use your calculator at this point? Yes, you could, and for the sake of time, I maybe would do that. But I don't want to set a bad example, so I'll just do it really quickly. Remember, you multiply this times this, and you get 45, and you carry. You multiply this times this, and you get 81, and then you add 4, so 85, and then you carry. And then you multiply this times this, 9 times 1, and you add 8. So that's 17, right? The number of decimal places are 2, so it would be there in theory. You usually do that at the bottom, right? Then it's distribute 1 to here, 1 to there, 1 to there, right? There is a placeholder that should go here first, and these should be collimated, so that when you're adding the second portion of this, you don't make a mistake. All right, 1 times 5 is 5. 1 times 9 is 9, and 1 times 1 is 1. So the end result would be a 5 here, a 10 here, carry the 1, 17 here, carry the 1, 3705. Right? The exact answer is $37.05, or if you want to be in math speak, it would be 37 and 5/100ths, because the 5 is sitting in the 100ths place. But nobody talks like that when they're talking about money. All right. Anyhow, that's exact. All right. Great to be exact. I don't know who is ringing my bell right now. UPS guy. Sorry about that. All right, the exact answer is $37.05, right? Now, an estimate is meant to get to the answer less arduously, right? As you can see, this can be quite complicated and sloppy if not on paper, right? So, unless they specify to which place that you're going to multiply, round to, you have the intellectual freedom to decide for yourself, right? Usually, right, just to refer back to the sheet that I made, usually when you multiply, you want to make it a little bit easier on yourself, right? So here we have this, right? For multiplication and division, these tend to be more about convenience, which means that you could round the parts, the factors, to different places if necessary. Right? So, they didn't specify which, so this is $1.95. Right? Let's say I rounded it to the whole dollar, the ones place. Right? Based upon the 9 here, right, what would I round this 195 to? Right? I might round it to just about $2, right? Right? That would be good rounding, right? Because according to the rule, if this is 5 or greater, then you increase that underlying digit by 1, so it's 2. And then you could put zeros in place of it. It's rounded up, right? This 19, right? Again, for the sake of convenience, I might round this to the tens place. Notice that's not consistently the same place. This is the ones place I rounded to. This is the tens place that I'm rounding to for convenience sake. All right. So again, making the judgment call based upon the 9 here. All right. This would be rounded to 20. And the decimal would technically be there just for the sake of comparison. Now, if the whole point of this is to make it easier on you, all right, there's really no need for these at this point, right? Things that are after the decimal point, they're not necessary. So what you really have here is 20 times 2, right? The $1.95 is really just about $2. The 19 is times 20, right? So that's $0, that's $40, right? The estimate is 40, right? Look at what the exact answer is for the sake of comparison. 3705, that is exactly the answer. The estimate is 40. It's reasonably close, one could argue. If I were going to be a little bit more of a twit, all right, I could have rounded this to the 10th place instead, all right? And that would still end up, because of a 5 here, it'd still end up being 2, all right? But then when I rounded this, I could have just kept it as 19. You know, it's more or less rounding to the ones place, because it would be 19.0. All right? I'd get a slightly closer to the exact answer estimate. Right? Again, the trade-off for convenience is accuracy. The more convenient, that is, the easier you've made the figures to multiply by, the less correct it is. Right? The less accurate it is. Anyhow, it's not a bad estimate. It's just to illustrate the process. All right. Look at example 2. I'm going to do this one a bit quicker. This is more adding and such. At a local discount retail store, Christie purchased a rug for $15.89, toothpaste for $1.49, diapers for $19.77, shampoo for $4.93, dog food for $12.88, and candy for 81 cents. All right, the cashier said the total bill was $69.51. Use estimation to determine whether the amount is reasonable. just for your own sake, if you actually added these all up, the exact answer should be, I believe, $55.77, right? Which means that the person who was the cashier either lied or just wasn't adding correctly, right? Anyhow, because you're not going to sit there and take out a tablet at the cashier's register because you get your head bitten off, what you do is you can just run an estimate in your head, which means that you're going to make nice round numbers out of each of these, right? $15.88, that, $1.49, that, and that. That technique of, incidentally, circling what you're going to use is what will be part of the discussion on Tuesday next week. All right, anyhow, when you're adding up decimal numbers, right, I would strongly encourage you, if you're going to write this down, to write it on graph paper, because if you write things on graph paper, you're less likely to make a mistake. It sounds crazy, but the anal retentiveness of writing the numbers in the boxes will make you more neat, right? And neatness often makes or breaks, the correctitude of your answer. You know, a kid knows how to add, subtract, multiply, divide, but they may have combined things inappropriately. So, $15.89, $1.49. When you add or subtract, everything has to be locked up like this according to the places. All right. When you add or subtract decimals, remember, right, they must align according to places. That's why graph paper is very handy. All right, even when you're estimating, I would start out that way. All right. 1977. $4.93 and $12.88. One more. 81 cents, right? This is some gobbledygook here. I gotta get rid of 81. Okay. When you add or subtract decimals, everything must be aligned, all right? All of the 100th place items are in a row, all the 10th place items are in a row, and so forth, all right? Now, if you added these, I believe that would be the exact answer. You could verify that in your own time, all right? Let us round these. Again, I would be more consistent when you're doing adding or subtracting. That means that you round things to the same places, all right? So, you could do it, you could round to the 10th place, or you could round to the 1's place. It's up to you. I don't remember which way I did it. Let's see. I did it both ways. Let's try the 1's place, just because it's a little bit faster. So, if I round to the 1's place, that's the much more convenient because I'm having whole dollars here. All right, I'm going to underline all of those. And I'm going to make a judgment call about each of these consistently in the 10th place. So I'm going to circle all of these. All right. 15.8. Based upon the 8, this would be 16, decimal point 00. All right. 1.49, based upon this 1 here, this 4 being here, right? This would be 1.40. All right. 19.77, based upon the 7 here, this would be 1 digit higher, which would in turn encroach upon that. So this would be, you can't fit a 2-digit number like 10 into a 1-digit space, right? So it encroaches. So this would be about $20. All right, 4.9 based upon 9 here is about $5. 12.8 based upon the 8 here is about $13. and 0.8 is about $1. Okay, again, these, if you're going to write it in decimal here, these really should be all collimated like so, because you don't want to add the wrong places together. They have to be consistent. Graph paper is what you should give your little kids, right? Not to really go off on a tangent, but if in school we give kids special paper for teaching them how to form their letters like that, why don't we give them graph paper that'll teach them math? We should, all right? But we don't do that, right? When you get into the profession of teaching little kids, give them graph paper. And yes, teach them to be anal retentive little calculators like that, all right? They'll make less mistakes because they have scaffold. All right, so zeros, down here is a 0, zeros, and the only 4 is a 4. Did I miss one of them? Oh, wait. Yeah. Oh, wait, I'm sorry. Yeah, I did miss this. All right, 1.4. Based upon the 4 here, we will round that down to just simply 1. Sorry. So that makes it even easier. I'm taking my own advice here. All right. Decimal point. 6 and 1 is 7. 7 and 5 is 12. 12 and 5 and 3 is 15. 15 and 1 is 16. So there would be a 6 here. Carry the 1. 1 and 1 is 2. 4, 5. So the estimate is $56. Right? Use estimation to determine whether this amount is reasonable. The dodo who was adding up here said $69. They didn't add correctly. All right. The exact answer, I believe, should be $55.77, and that's a pretty good estimate because it's pretty close, right, to the exact answer. All right. So beware. All right. When is it? 10:38. Okay. Now let me just discuss formulas very quickly. Sometimes, and this will be again more appropriate for discussion next week with word problems, sometimes you need a formula. You get a couple of things, right? If you see the word is in a word problem, automatically use an equal sign. If you see the word per or an or in, use something called a rate, right? Which is something that basically converts units. Right? It's more or less a fraction. It's fraction-like. Right? Meaning that there's an obvious top and an obvious bottom. Right? These are some rates that would be good to know. Right? There's speed is a type of rate. There's mileage. And then there's prices. So famously, in the case of speed, there's distance divided by time. And it ends up being basically miles per hour. Right? For mileage, it's very similar because it involves distance, but it's distance over, this is divided by gallons or volume. Right? So very often that's miles. In the United States we use per gallon. And the rest of the world it would be liters. Okay? And this line is understood as per, which is, again, that's division. The top divided by the bottom. When we're talking about prices, a lot of times you have some value, whatever it is, over a unit. The value is the dollar value, you know. So that's something like dollars per gallon, again, if you're going to use some unit. Remember, the dollar sign really should go in front of the number. I know a lot of times people nowadays erroneously put this in the back. Don't do that. It goes in the front. Right? No sign in the United States ever puts the dollar sign after the back. Why? It's not measured, it's counted. It's different. It's not a measured unit, it's a counted unit. Right? Okay, now if you look at example 4, let's see, is that a good one? Yeah, example 4 is a good one. Because it has a couple of different parts. I just need the space, so I'm going to clear that out. All right. At a local discount retail store, no, not that one, sorry. That was 2, look at 4, please. Okay. The Martellos traveled 1,276 miles from their home in Springfield, Missouri to Yellowstone National Park. They went on vacation. All right, and they went that many miles. All right. Part A. If their trip took 19 hours of driving, all right, estimate the average speed. That's just what you see in red here. Right, which means that without them explicitly stating, you would need to know that there's a formula involved. You're going to divide miles by hours. But you're going to try to estimate it. So you're going to make these numbers easier on yourself. Rather than doing 1,276 miles exactly divided by 19.9 hours, you're going to make this more convenient. Now, this is why I say you need to know your multiplication tables by heart, because if you do that, you very strategically will change these figures to something that divide nicely. You make them divisible. All right? You could divide almost anything by anything, but you want to make it easy on yourself if you're not using a calculator. So make these round numbers. All right? Again, to emphasize, when you're doing multiplication or division estimates, all right, it's more about convenience. You may round to different places, all right, to make it easier. All right? So, let's start with the bottom because it might be a little bit more obvious, right? Let us say that we round this to the tens place. So based upon the 9 sitting here, what is this approximately in terms of time? This is about 20 hours. Okay? Now, if I want these to divide nicely, just for the sake of strategy, all right, I'm going to try to make this into something that is an even number, you know, as well. So, remember, the trade-off is if I make it too convenient, then it might be very drastically different from what the exact answer is. But we'll try to be reasonable, right? I wouldn't just round this to the thousands place. That might be really cheating. So, let's maybe round to the hundreds place, right? It's up for debate really whether you do it that way or a little bit more precisely. Right? But this top would be about what? Based upon 7 here, I would change this to 1,300. All right. If I made it 1,300 miles, that would work, all right? But the math isn't going to be super easy if you do that, right? So you could go a little bit further around to the tens place and make it 1, 2, 8, right? Because they both end in a 0, they're both even, this isn't going to be bad, right? So I'm going to stick with what I did, right? And I'll show you a shortcut. Right? When you have it written in this orientation, one thing above the other, you could cross out pairs of zeros. So you're going to cross out that pair, and that means that what you have is now you have 1,300 over 2 instead. It's just essentially asking you, what's this cut in half? Right? What's 13 divided by 2? All right? It would be equal to 2 goes into 13 6 times with a difference of 1, so I'm going to squeak a little 1 in here for short division, because it would have been 12, right? 13 minus 12 is 1. And then 2 goes into 10 exactly 5 times. So this is miles per 1 hour, if you like. Right? You could dismiss the bottom if you'd like, right? But that is their average speed, 65 miles per hour, which is reasonable, right? All right, now if you answer B, if their car gets 52 gallons of gas, uses 52 gallons of gasoline in that distance, all right, that same 1276 miles, but use 52 gallons, estimate their average gas mileage, using what is in blue more or less here. Okay, so 1276 miles over 52 gallons for gas mileage. All right. Again, since you're doing division, it's about convenience more than consistency. You could round to different places if it makes it easier, so you could apply shortcuts. All right. So, just because I need the space, I would round that to 50. That's more or less rounding to the tens place here. So that would be about 50 gallons. This is a nice round number. And again, I could stick with this hundredths if I like. All right. Even numbers will divide nicely. All right. So that is based upon 7, again, about 1,300 miles. All right. Once you have it in this orientation, something over something else, the shortcut is you could cross out pairs of zeros. And it basically becomes 130 divided by 5. Now, if you remember rules of divisibility from childhood, anything that ends at a 5 or a 0 would divide pretty what is divisible, right? All right, it's going to divide nicely, no remainders, no decimals. All right, so just do it. Do short division. All right, 5 goes into 13 roughly 2 times, which is 10. The difference of 13 and 10 would be 3. So I'm going to squeak in a little 3 short division to then figure out the next digit. 30 divided by 5 is 6. So it's 26 miles per gallon. All right. Also reasonable. All right. And then the last one is if the cost of a gallon averaged $3.99 per gallon, estimate the total cost of the gallons used. Well, we just estimated, well, they just told us that it's 52, right? So, let me show you a little trick here, and I can get this out of the way now. All right. Look at the way that this is written, $3.99 per gallon. If I wrote that in more math style of a rate, that would be $3.99 over 1 gallon, right? To multiply then by the number of gallons used, 52 gallons, all right? What would happen is there's a cross cancellation effect, Right? The unit here, gallon, as long as it's above the line, will cancel the unit down here as long as it's below the line. This happens when you have a multiplication. Why am I multiplying? I know it didn't explicitly state it, because if it's 1 gallon, it's exactly $3.99. So one would estimate that more gallons is it's a higher price. Now, you could do brute force $3.99 times 52, or you could make it easier on yourself. You could say this is about $4 based upon rounding rules, and you could say this is about 50 based upon rounding rules, and then do 4 times 5 is 20, and then attach the extra 0. So it would be about $200. You're left with the unit that you want, namely dollar value, all right, because of the cancellation effect. Okay? And the very last thing is just to show you how you would estimate a number of kernels here. If you were going to, this is example 7. All right. Estimate the number of corn kernels in the top layer of the accompanying photograph. I'm going to get rid of this because I don't need it. Take a look at this picture. I'm going to need to back it off a little bit. All right. How would you go about the process of estimating in this respect? All right. You're not going to sit here and count all the kernels. All right. What you've noticed is that they've overlaid a grid that's superimposed on here, and that means that there is, let's see, 1, 2, 3, 4, 5 boxes this way. 1, 2, 3, 4 boxes this way. You have a rectangle that is basically 4 by 5, which means that there are 20 boxes. Right? Rather than count all of them, an estimating technique would be, well, go to the first one, say here, and then count how many corn kernels you see in there. Right? So I'll try. All right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, maybe 20. So it's about 20. 20 kernels, is that how you spell? Yes, per box, right? That's a rate once again, right? So if we're going to translate this into something that was similar to what we were just talking about, a rate that is something written in the style of a fraction, if it is 20 kernels per, that's that line, box, one box. If I multiply that amount of 20 times the number of boxes times 20 boxes, all right, there is again this cross cancellation effect, right? The unit is box up here above the line, and the unit down here is box below the line. That means I'm left with the unit that I want. All right, this is something that will be more relevant when you get to chapter 7, all right, or if you've seen chapter 7, all right? And it is essentially 20 times 20, which is 2 times 2, which is 4, with an extra 0 and an extra 0, 0, 0. That's about 400 kernels. All right? It's a good estimate. Okay. All right, the book had done, they estimated 18 instead of 20, but so be it. All right, so they got 360, but it's up for debate. All right, that is it. All right. Basically, since we are, this is for Thursday, section 1.1 and 1.2, what you should do is work on section 1.1 and 1.2 in my lab, and the prerequisite as well, all right, for chapter 1. Okay? Thank you guys for sticking with me. I'll see you again on Tuesday. Be careful out there.